Hi everyone, so let's start off from where we left off. And basically we were talking about the electromagnetic spectrum, right? So it's shown here. And basically this is just a spectrum of radiation, right? So as we said, there are many different types of radiation energy. So we have light energy, heat energy, sound energy, potential kinetic energy, all of those different types of energy, and we have light energy, right? So here we're talking about light energy, and according to Einstein's law, this light will all travel at the same speed, at the speed of light. So basically we have different energy of traveling in waves from the high energy part of the electromagnetic spectrum, so around here, X-rays, and the low energy part, so around here, so radio waves and things like that. So basically, if you want to have a look at the wavelengths, we have nice big wavelengths here, and as we get along, we have smaller and smaller and smaller and smaller, and then we get to tiny, 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 tiny gamma rays over here. And you can even break up the visible light spectrum. So we'll just do that in the next slide. Alright, so this is all revision, this as well. So let's get to the visible light spectrum here. And it starts off at a red. And this is, again, bigger wavelengths, right, to a purple, which is tiny wavelengths. Okay, so let's just go over the flame test, right? So here we have the flame test. Basically, different types of ions, different types of metal atoms can form different types of colours when you put them in a Bunsen burner flame, right? So sodium goes yellow, potassium goes purple. We know this experimentally. Okay, so the flame test, we're putting a metal into a flame, the electrons are jumping, absorbing energy, going from a lower, more ground state to an excited state. So let's just say here we have our ground state. That would be the lowest energy, so energy is going up. Let's just say we've got energy, energy, and then it's going up. So our electron starts off around here. It absorbs energy, and in doing so, it goes up. However, this energy state is unstable. We know that because electrons want to be in the lowest energy state, and they only jump up in the first place because they're absorbing energy. This is defined by this equation, the amount of energy it absorbs, and then it will jump back down to the lowest energy state. And in doing so, what it does is releases energy of the same wavelengths or energy that it absorbed. Okay, so the higher the wavelength, so the larger the wavelength, the lower the energy, right? And the smaller the wavelength, the higher the energy, right? So you should know those two things. Now, let's just quickly have a look at the flame test in a little bit more detail. So, we have reds, as we said, were a bit lower energy, larger wavelength, and purples were high energy and short wavelengths. Okay, so our basically each energy level, you could think of it as like an orbital, 1s2, yeah, 2p6, etc., etc. Okay, and then they're all defined by a specific amount of energy. Okay, now if we have something jumping up, absorbing energy, and it happens to absorb a lot of energy and jump all the way to level energy 4, it's going to want to jump back down. Now, what might this high energy be? Okay, quite a bit of energy. We might think that it corresponds to more of a violet colour, right, in terms of the visible radiation that we see. Okay, so when it's jumping down, it might actually do so by releasing violet light like potassium and jump right down. Or it might actually go to the next, it might jump to level 1, for example, not completely to the ground state, and release blue light. And then it might release red light and jump to the ground state. It might release light blue light and then yellow light. So it might actually do these things all at the same time. Some electrons might go all the way down from the top. Some might go through different pathways. Okay, so here we go, different alternative pathways that it might go down. So you can see that there can be lots of different lights that the one metal may release. Okay, so what are the limitations? Well, we can see from there that the limitations are very few elements are excited by the hottest flame. Okay, we know that the flame test is useful for a limited number of metals. Now, why is it useful for a limited number of metals, you might ask? Metals actually have one electron or two electrons in the outer shell, well, group 1 and 2 metals. Okay, so they actually don't want their electron in their outer shell. Okay, they're not very electronegative, we might say, because they want to get rid of their outer shell electrons. So it's actually quite easy to excite them and remove that electron. Not much attraction between the nucleus and the outer electrons. That's why it excites groups 1 and 2. Now, only some metals produce a unique colour in the flame, so that we're able to identify it in the flame tester. This makes sense if we think back to here, because barium, for example, and sodium, for example, both produce a yellow flame. Calcium's not pictured here, but strontium is dark red and so is calcium. It's sometimes difficult to tell those two apart. Okay, so it's rare that we'll have such a unique colour, like copper produces a very unique green. Okay, so a number of electrons can be excited to a number of different energy levels and take multiple paths back to the ground state, right? Producing a mixture of colours. So in this case, we might have a purple being released, a dark blue, a red, an orange, a yellow, all of these being released simultaneously. So we might not actually be able to see these colours, right? The colour that we will see is a combination of all of these colours. Yeah, so it might end up being masked, for example, and look purple if purple masks the other colours if it's stronger. So we need some way to find out what individual colours are being released. Impure samples, right? We might have something like, let's say, sodium with a bit of copper. Most likely will go green because of the copper in there, and the yellow sodium will be masked by the impure copper in there. Okay, is there a way that we could actually get a profile of all the light emitted by electrons? So is there a way we can separate these colours produced by the flame test? Well, the answer is yes. And that's when we move on to our next technique, and that's atomic emission spectroscopy. Alright, so since the flame test has a limited use as an analysis method, there are two modifications made in the AES, right? So made in this technique to overcome the problems of the flame test. What do you think they are? So there is a hotter flame. Remember that there are only some elements that are excited by the hottest laboratory flame, right? Because some metals want to get rid of their electrons so much that it's easy to get them excited and jump to the next energy level. But if we have a hotter flame, we're inputting more energy, we can make electrons jump. Greater gaps in energy, greater delta E. Okay, so we have a hotter flame. Now the other thing, I think some of you might have guessed it, maybe those in physics, is we can actually pass the light through a prism. You'll probably like my GIF, very nice. Okay, now the different energies emitted, right, are broken up now. A prism breaks up the wavelengths into individual wavelengths. Okay. Now, this is atomic emission spectroscopy, and this is a step up from flame tests. Okay, so if we watch these little YouTubes on it, we'll see how we go. Alright, so we have ground state, level 1, excited state, level 2 and 3, electron at a ground state, energy coming in, so in the form of heat from the Bunsen burner flame. Electron being excited, jumping in energy level, unstable, needs to go back down, right, so jumps back down. Now skip through a little bit, and it releases a photon of light, or it releases the same wavelength or energy as it absorbed. Okay, now the next scenario is where we've got, so that's what we see with our eyes. Let's see if we add more energy. So this is talking about the hotter laboratory flame. Violet. And we excite the electron and it can jump up to level 3. And then it jumps back down, releasing violet. Okay, so we'll just skip through that. Unstable electron jumps back down to ground state and releases violet light, which we see. Alright, now let's watch the other one on atomic emission spectroscopy. Okay, this shows you that hydrogen, this is actually the light that hydrogen releases, and to us, to the untrained eye, we might just see yellow, purple, but in fact, we can break up the light and we see it as some emission lines of red, blue and purple. The light from hydrogen consists of only a few wavelengths. Helium. Helium's a little bit more. Let's go through. Mercury. Three different lines. So you can start to see that we can actually split up the different wavelengths of light. Okay, so let's go through the different parts of atomic emission spectroscopy. So you should be having, while we're going through this part, you can be, say, filling in the gaps on this worksheet, right? So spectroscopic analysis, the one that I gave you guys. So we're pretty much up to around here, atomic emission spectroscopy. Okay, so you can fill in the gaps there, or you can just write your own notes in your book. Okay, so basically we know that we've got a flame here, and we've got it's sort of a hotter flame to what in the flame test, sorry. Okay, so we've got our sample here, we heat it. Now the flame is a lot hotter than in the flame test. Then we have a slit, and you might ask, why do we have a slit? Well, you can see we might be getting lots of different light, but we want to focus it, right? So we want to focus, we want to have just the parallel beams of light, okay, from the incoming light. Now we have a prism, and that's obviously to disperse it into the individual colours, and we get what's called an emission spectrum, right? So we have red, yellow and blue, and sort of indigo and violet. So if we just looked at this element through a Bunsen burner flame, and without the prism, we might have just got maybe a purple or something that masks it, or a red. I'm not sure which one would mask what, but if we actually use a prism, we can split it up. Okay, so the spectrum of light from highest energy, which is right, yeah, to lowest energy and largest wavelength, red. Okay, so here I want to focus on emission, right? And now we have a couple of elements here, right? And we've got hydrogen, mercury, neon, and hydrogen here. And basically, what do you think the difference is between this and this? Okay, so these are the lines that are called emission lines, and it's basically what energy is released. So we remember, that we get an emission spectrum for each element, ranging in when it breaks up each of the different types of light released. So this is our emission spectrum up the top of 3 different elements, and then here we have every colour, but we have some actually some light taken away. This is what's known as the absorption spectrum. Okay, now what I wanted to show you guys was a few different types of emission spectrums. So here we've got hydrogen right here. Let's skip through helium, lithium, beryllium, all the way up to the top. So it's pretty much, this is all experimental evidence. You can see we go to titanium, releases lots of light, nickel, copper, arsenic, right? Strontium. Okay, this is sort of an interactive website. We could try this. Emission lines of beryllium, it releases one line at 467.3 nanometers. So let's go to 467.3.
Now 436.1, 436.1, that's probably over here. Yep, and then we have 527.0, 527, yep, and then we have 440.7, and we could go somewhere there, and we've got 482.8, 482.8, sorry.
And we could compare to the actual spectrum, and you know, pretty good, not bad actually. Didn't tell us really all of them, did it? Okay, so you know, you guys can have a play around with that. Lots of stuff online, but basically you just need to know that different elements release different lines. Now I want you guys to focus on this bottom part, the absorption spectrum. You'll notice it's hydrogen, so you'll notice with the top one we've got how many different lines? 1, 2, 3, 4. And we've got a purple line here, high energy. We actually missed that purple line here. We've got the blue line here, missed the blue line there. Green line here, missed that green line here. I think you know where I'm going. Red line here, missed the red line there. So I want you guys to just talk about this for a couple of minutes. Why do you think that in the emission spectrum, this is emission, right? We have a certain number of wavelengths that are released, but in the absorption spectrum, we have sort of the opposite, right? Whatever we emit, we miss in the absorption spectrum. So I want you to just talk about that and then come back to the class. Okay, so if you said something along the lines of it's because whatever it emits, right, it will have absorbed. Remember, we have the lowest energy state and we have a higher state. It absorbs, let's say delta E equals 1. It absorbs it, right? It absorbs that energy and it goes to a higher energy state. Remember, energy is increasing as you go up to the next level. This might be level 1, this might be ground state. Now, it releases the same amount of energy. So we're looking at releasing, we are looking at this, and for absorbing, we are looking at this, right? So it will be the same energy absorbed as it will be released. So let's look at atomic absorption spectroscopy, right? It's not emission anymore, it's absorption.
This animation of a flame spectrophotometer will provide an idea of how the machine works. The analyte is taken into the nebulizer where it is vaporized and conditioned to provide the best sample for the flame. The radiation source sends light through the flame and into the monochromator.
So we have sucked up our sample here, right? Through here, our analyte goes in through a capillary tube and basically we put it into a flame. Similar thing to emission, right? Similar thing so far. The flame again is hotter, so we can analyze many different types of metals, right? Still just metals.
In the monochromator, the beam encounters a series of mirrors that separate the beam from any background light and noise that is not necessary for analysis. This filtered beam finally hits the detector, which relays the data to the analysis software.
So you can just imagine that a certain amount of light will come in here. Now, our sample will absorb some of that light. So the light that is then, the light that's left that hasn't been absorbed will be picked up by the detector. Okay, so our sample, say if our sample's copper, it'll absorb the same light as copper releases, and copper releases green light, so we'll absorb green light at the wavelength that green light is. Go to green light, so green light is at about 500 nanometers. So we could say our copper will absorb at 500 nanometers and we expect to have a gap here. Okay?
This is the gas that feeds the flame. These are the lamps that provide the source of radiation. The lamp is specific to the analyte. The analyte is taken into the flame by this capillary tube. Data collection is performed by software installed on a computer. This demonstration will use a sample of copper. First, start by cleaning the sample capillary with a chem wipe. Then, insert it back into the sample to be aerosolized, mixed with gases, and released into the flame. The flame turns a green color that is distinctive of copper. Waste is then siphoned off into a collection bucket. The data is then sent to the computer for analysis.
Now, it's a little bit of a different setup to AES, where we have a light that's emitting a wavelength, right? to excite electrons. In AES, we don't have, sorry, let's skip that. In AES, we don't have a light. We just have our metal, and we've just popped it in the flame, and all we want to see is, after the electrons are excited, what type of light is released. Now, in AAS, or atomic absorption spectroscopy, we are releasing light, right, to our sample. Our sample will then absorb some of the light that's released, and we want to see how much it's absorbed and at what wavelength. Okay, so we have this thing called a hollow cathode lamp, and basically if we've got copper in the flame here, we've got copper in our lamp. Our lamp is actually made out of copper, a cathode, right? And this will obviously release light, green light, that will be absorbed by our sample. So the sample is dissolved in acid because we want to convert the metal into ions. Then we spray the ions into the flame, and this converts it into atoms, right? Okay, so it's a very hot flame. And here you can see, when we go to VU, we're going to have a look at this. This is our atomic absorption spectroscoper, and we've got the sample solution sprayed into here, which is actually where the flame is, and the light will come through these holes. Okay, and then we've got something called a monochromator, which selects the wavelength of light. So it might select 400 nanometers for copper, for example. Okay, and then we've got a slit to select for parallel light, and then we've got a detector. So how can we use AAS as a qualitative, how can we identify metals using AAS? Basically, each atom will display a different absorption spectrum, right? It's basically like a fingerprint for the atom. Here you can see neon looks like this, mercury looks like this, and hydrogen looks like this, all different. Basically because they have different numbers of electrons and they have different numbers of protons in the nucleus, right? So since they have different energy levels, the spectrums are all different, right? Now, that's all well and good. We can use a fingerprint to find out what it is, but while atomic emission spectroscopy and the flame test are both only qualitative techniques, AAS is actually quantitative as well. How do you think we could use AAS to determine how much metal we have in a sample? Think about it for a couple of minutes. Okay, first we need to determine the wavelengths that our metal will absorb, right? So we pass white light through a pure substance. Let me show you what this means. Let's see if we've got copper here. We know that white light releases all of the different wavelengths, so let's draw them. Okay, and then we have copper here absorbing, and depending on how much, the more you have, the more absorbed. Yeah, the higher the concentration, the more absorbed. Okay, but say if we've got copper here, we will have some red coming out. Red won't be absorbed. And green, oops, I chose a different green then. Oh no, I didn't. Okay, so green, actually some of it might be absorbed. Let's draw it like a dotted line. Some of it's absorbed. We know how much went in. we know how much light went in, we know how much light's coming out, and we can draw what's called an absorption graph, right? So we have absorbance on the y-axis, absorbance, and on the x-axis we have our wavelengths. So we have it about 500 nanometers. So this would be nanometers. We get not much absorbance here, but then we get a peak at 500 because copper absorbs at 500, right? And this is all done by the detector. It's all done, you know, you don't have to draw any of that. It's all automatic. Okay, so let's just rub all this off. Okay, so let's keep going through it. Now, alright, let's see if I can go. Okay, now the detector then prints an absorbance profile, as I said. Okay, so here we have two components. What can we say about this? We have two graphs. Let's look at this graph. We know that it's a single compound, compound X, right? So where does compound X absorb the best? And this might be an exam question, and we say that it absorbs the best at around here, which is about 255 nanometers, let's say. 255 nanometers, we have a peak, so that's peak absorbance, best absorbance here. Now we might also say that it absorbs at 400 nanometers, around about 400, so here. Okay, now if we look at our yellow, our red and our blue, right, our yellow, red and blue, we can ask where do they absorb best at. Our yellow absorbs best at here, about 420. Our red absorbs best here, about 520. Maybe 540. And our blue absorbs at 620. Okay, but if we're going to look at how much red there is, we need to make sure that it doesn't overlap with our yellow and our blue, so we would pick about 500 nanometers to do that. But let's get, we'll get there. Okay, so quantitatively using AAS, we use a hollow cathode lamp made up of the metal we wish to analyze. The atoms being analyzed are present in the flame, absorb some of the light. The amount of light absorbed will depend on the concentration in the sample. The light that has not been absorbed will pass through the monochromator, and the monochromator will then select one of these wavelengths to pass through to the detector. So at first we will select, like say if we want to look at the concentration of compound X in a sample, we will go, it absorbs best at 250, right? So just bear with me. It absorbs compound X, absorbs best, I don't want to do green, it's probably can't see it. Compound X absorbs best at 250 nanometers. So we plug that into our monochromator and we can see the absorbance at 250 nanometers. Now let's say, this is where I'm leading to, similar to chromatography, we have a chart. Now, we have our concentration of our standards, concentration, so compound X might be, let's say, copper, right? So we have standard concentrations of copper. We have one at 1 millimolar, one at 2 millimolars, and one at 3 millimolar. And if we look at absorbance, we might have absorbance 10, 20, and 30. And then we have an unknown. We want to find out the amount of copper in a particular pipe or in a sample of seawater or whatever we want to do, or in food to see if it's at a toxic level. And we might have X concentration, we don't know what it is, so question mark, and we have absorbance of 25. Now, allow the students some time to draw out the calibration graph. Okay, so once you've done your calibration graph, you should have plotted absorbance versus concentration. Yeah, oops, conc. And then we might have 1 here, 2 and 3, and then we have 10, 20, 30, 1, 2, 3, line of best fit, oops, no extrapolating, and we should get a concentration at 25, which gives us a concentration of about 2.5 millimolar. Okay, so it's exactly the same as creating our calibration curve for chromatography. Okay, we use a hollow cathode lamp, as we said. Okay, so the intensity of the selected light will then be measured by the detector. We can create a calibration graph. We have our unknown sample. Okay, and the sensitivity of atomic absorption spectroscopy is in parts per million or parts per billion. Okay, so here we have a past exam question. Okay, analysts determine the concentration of calcium ions in a water supply using AAS as the analytical tool. Okay, a simplified diagram of the AAS is shown below. What particular characteristic is needed by the lamp providing light source S? So remember in AAS, okay, first of all, I want you guys to think about it. A couple of minutes. Press pause if you need to. Okay, so remember that the light source in AAS is called a hollow cathode lamp, right? Hollow cathode lamp. And what's so special about this light source? Well, it is made out of, I'm just going to write hollow cathode. It's hard to write neat with this. But it is made out of the same metal as what's being analysed. So let's just stick with our copper. It would be made out of copper if we were analysing copper, because basically it needs to emit what the sample absorbs. It needs to emit wavelengths of light that will be absorbed by calcium atoms. So in this case we're looking at calcium. Oh yes, calcium ions in a city water supply. Or we could say the lamp must emit emission spectrum of calcium, or the lamp must emit wavelengths absorbed by the element being analysed. It must be a calcium lamp. You could write any of these 4 things or something along those lines and you'd get the point. Okay, now next thing, 33% of the state got this right. I don't know if you can see it, so I'll just read it out. The graph below shows the absorption spectra of 3 food dyes. We've got blue number 1, right? Red number 2, and yellow number 4. Okay, which one of the following is the best wavelength to determine the concentration of red number 2 in a mixture containing all 3 dyes? So think about it. In a mixture containing all 3 dyes. Okay, so if we have a mixture, we would have our yellow, our red, and our blue all in the one sample, all in the flame, right? All in the flame. Now, we have our light being released, yes? And we have our yellow, red and blue. Now if we chose the peak of red, which is what you usually would, so around 520 nanometers, or say 530 nanometers, what would be the problem with this? 540, sorry, so 540 nanometers, what would be the problem with this? Well, we've also got blue that absorbs at that wavelength, so once we get our absorbance, we could have absorbance of 30, let's say, absorbance of 30 at 500. We can't be sure that all of this is our red. Some of it will be our blue because it's in a mixture. So we basically need to choose a wavelength that doesn't overlap with the other wavelengths. So around 500. So the answer is B. If you guys thought it was B, that's good. Next question. The UV visible spectrum of a solution of certain compound is shown above. Consider the following statements. Statement 1, and the question's asking which are true, so kind of go and statement by statement, okay? Try and read it by yourselves, but let's just go through it, okay? So the compound of light absorbed by a solution depends on its concentration. That's very right. The amount of light absorbed by a solution depends on the wavelength of light used. Also very right, sorry. If we had 350, it wouldn't absorb much, but at 250, it would absorb a lot. The spectrum is a result of electrons falling back from higher to lower energy levels. We know from higher to lower, it's emission, not absorption. So that's incorrect. Now the next one, the concentration of a solution can only be determined by UV visible at 250 nanometers. Can we only determine it at its peak? No. It's more sensitive at its peak. That's why we choose it. But no, we can actually go at 400, 350, whatever. Okay, as long as it has some absorbance. So, oh sorry, so that's wrong, so it must be 1 and 2, which is A. Okay, we use the, if we can use any wavelength, why do we usually use the optimum? As we said, because it's more sensitive. So uses of AAS, I'll give you guys a minute to think about this. Why would we use AAS? Obviously it'll only be for metal samples. So what's this showing? Analyzing toxic metals in food, for example mercury. We could also look at the urine in blood to detect deficiencies in metals or toxic metals. And we have a power plant over here which is testing for pollution in air, soil and water. Another question. A brand of fruit salad makes the claim that 100 grams serving contains 6 milligrams of sodium. AAS was used to check this claim as follows. A 50-gram sample of the food salad was treated in such a way to extract all the sodium. The volume was blah, okay? A 10 ml sample of this solution was then accurately diluted to 100 ml for analysis. A set of sodium standards were then analysed, followed by the diluted sample. The results are shown in this table, right? So didn't really have to read too much of that. We can have a look. The solution concentration, we have our standards, their absorbance. I want you guys to create a calibration curve. So press pause and let the students create a calibration curve. Now the answer should look about like that, okay? And our test sample would have a concentration of about 13.5 parts per million. Okay, and converting that back, right? So just give them a minute to try and convert back to find the concentration in the test sample, and they should get an answer of this. Okay, another practice question. Okay, you guys can do this in your own time. The answers are all in the books. Okay, now, in the slides. Now, are we always going to have to analyze metals? That's the question. The answer is anger. No, we can actually use UV visible spectroscopy.